Okay. Well, Bill Unruh gave a nice warm-up to my talk. I'm not sure that there's anyone who hasn't already been convinced by the case for information loss, but in case there are a few who are still sitting on the fence a little and didn't quite have time to digest everything over lunch, I wanted to lay out the case for information loss. I mean, the arguments for it, the arguments against it, et cetera. So the key element of the story, I think, is entanglement. Now, if you have a quantum subsystem that you can break up into two subsystems, just generally in quantum mechanics, entanglement is absolutely ubiquitous. I mean, if the subsystems are interacting in any way, even if you start them out in a product state, they'll rather quickly become entangled. So it's a certainly ubiquitous feature of quantum mechanics, but I would say that it's really an essential feature of quantum field theory. Specifically, in quantum field theory, this is a space-time diagram. This is some moment of time, this red slice, and I've drawn two regions here that whose union encompasses this time slice. So I can break up my system of observables for the quantum field as the observables in this region and the observables in this region at this time. And if I do that to my two subsystems, then I claim that completely generally, in any physically reasonable state of the joint system, the two subsystems that I've talked about that are right up next to each other, essentially touching, are always going to be entangled, and very strongly entangled. In fact, if you don't put in an ultraviolet cutoff of some sort, infinitely entangled. Said another way, in all physically reasonable states, there's going to be very strong correlations between the observables in one region and the other. These, of course, the observables here all commute with the observables here, but the entanglement is very strong, and there'll be extremely strong correlations, particularly between observables close to here and observables close to the other region on each side. And I'm just saying that that's true. Any two such regions, any space-time, whatever. So in particular, an example that all of you, I think, of this that all of you are very familiar with is in Minkowski space-time. If I were to draw this with no boundaries here, same set of observables, so it's the same thing, then I have the two Rindler wedges here, and the observables are very strongly entangled in any physically reasonable state, and that is a key ingredient in accounting why observers in a single Rindler wedge see a highly mixed thermal state when the quantum field, in fact, is in the pure Minkowski vacuum globally. So this entanglement is a very key element of the Unruh effect, and the Unruh effect would make no sense without that entanglement. Well, the story that I just said completely generally is going to apply if we have a semi-classical situation where we have a black hole. If you've formed a black hole, they'll automatically be in exactly the same way, in quantum field theory, in any physically reasonable state, strong entanglement between the state of the quantum field outside the black hole and the state inside. And in the same way as this entanglement in the Rindler-Minkowski case is very closely related, intimately related to the Unruh effect, in this case, it's intimately related to the Hawking effect. I'm not quite going so far as to claim that there's no way you could get the Hawking radiation if you broke this entanglement, but it would be awfully difficult and awfully artificial, I would claim. Now, this isn't the only entanglement due to Hawking radiation that you could have. This arises, of course, on very small scales near the horizon. That's not by any means the only entanglement you might have between the inside and outside of the black hole. You could collapse the black hole with Bell pairs or some other highly half of systems of Bell pairs, or even more entangled state of matter here that's entangled with matter that you've put safely far away from the black hole, have this matter collapse. You've got a lot of entanglement just due to that, and you really could, if you were very careful, make the entanglement entropy of the matter that you've used to form the black hole comparable to the entropy of the black hole itself. This is before any Hawking radiation starts. You could make that degree, order of magnitude degree of entanglement. Yes?
Sorry.
But the only way I know of doing that is to take a time comparable to the evaporation time, or are you saying that
well, if we're going to
avoid that?
I haven't thought about this. If you really wanted to make entanglement entropy comparable to the entropy of the black hole, you'd really have to do that carefully, and I haven't thought about how much time that would take. You certainly might be right on that, but I can certainly produce a healthy amount of entanglement, not necessarily anywhere close to entropy of black hole, by in a
maybe
very simple pairless manner. Yeah, and I could undoubtedly do half the entanglement entropy or something in a time much shorter than evaporation time. Okay, so if you take into account classical general relativity, the Hawking effect of the quantum field in this semi-classical background, and the back reaction of the Hawking effect on the semi-classical space-time, you produce this sort of space-time diagram that actually I was surprised not to see a lot of drawings of. John's talk had a bunch of them, but not too many of the others. But I want to go over this carefully. This is the semi-classical picture and the semi-classical prediction, I can unequivocally say, of what happens in black hole formation and evaporation. And of course, the rest of the talk will be, what is or could be wrong with this picture, and why would one also otherwise think this must be wrong or might be wrong. Okay, so I've drawn here, matter collapsing to a black hole, and again, this could be matter that's very entangled with matter out here, if I want. But I'm assuming that initially we've started in a pure state of the whole system. So the matter, according to, these quantum corrections are incredibly tiny locally. We collapse to a black hole. The classical or semi-classical picture would give you that you form some singularity. I'll get back to this a bit later. But way before you form the singularity, you form a black hole, and I've drawn in the event horizon here. Of course, this is a conformal diagram, so not at all to scale on proper times and so on, as seen by various observers. But once you form the black hole, the Hawking effect takes place, and there's a tiny negative flux of stress energy into the black hole due to the quantum field corrections, that goes into the black hole and very gradually reduces its mass. Radiation comes out, and in the it's an absolutely well-defined semi-classical calculation of what the quantum field state would look like out here in this process, and it is a thermal state. The radiation out here is completely entangled with stuff that's inside the black hole. I'm just making the assertion that's what the semi-classical picture says. I'm also, I guess, going to be making the assertion that is or should be what happens, but I'm not making that statement now. So the situation here at some intermediate time as the black hole has begun to evaporate, of course, is that you still would have a pure state on this time slice, but you've got correlations between the outside and the inside of the black hole. So if you just look at the observables outside the black hole, that subsystem is in a mixed state because of the entanglement and correlations. So the semi-classical picture says, of course, that the black hole continues to evaporate, and a time of order m cubed will evaporate completely, leaving behind, presumably, empty flat space-time. And the whole point is that it's only this part that evolves up to here, so you end up with a quantum state up here that is still entangled with the stuff that used to be inside the black hole that has now disappeared, and in that way you have a pure state evolving to a mixed state. Now, a priori one can ask, I mean, this is the semi-classical picture. Where would one expect on grounds other than one doesn't like the conclusion, this picture to be wrong? And of course, one certainly would expect the picture to be wrong when you're getting locally to curvatures near the Planck scale. And I've kind of sketched this in with a little line here, way, way off scale, because of course it's much, much closer to the singularity, almost whatever my conformal factor is in this diagram. So certainly when you're close to the singularity, which includes the last Planck time or so of the black hole evaporation, there's absolutely no reason to take this picture seriously. But conversely, when you're well away from the Planck scale here, 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 etc., there's no obvious reason why this semi-classical treatment would break down. I mean, again, that's, I think, a straightforward assertion, and I've already said that this would give you dynamical evolution from a pure state to the mixed state. I mean, this is the Hawking argument of nearly 40 years ago. Nothing particularly new in anything that I've just said about that. So the question that I want to ask is, what is or could be wrong with this picture? So, here is the same semi-classical picture, and I've divided what could be wrong with this picture into 4 regions here, which I think cover all of the logical possibilities. I mean, you could have more than one place where it breaks down. I mean, the semi-classical approximation may break down, picture may break down here, here, or other places too, but that's not going to be very relevant to the information issue, or pure states going to mixed states. So I think, these are the places, distinct sort of regimes where it could break down and change the conclusion of information loss. So let's go through these possibilities. So one possibility is that you actually never form a black hole. I've just drawn in this dotted red line here to guide your eye as to where the horizon would have been in the original picture. So the original picture is pretty much unchanged here, but it's drastically changed here because somehow, just as this collapsing star or whatever it was, it would have been predicted in classical general relativity to have formed a black hole, it transforms itself into something else. I mean, this is the fuzzball scenario in particular. And you don't actually have a black hole, and now there's clearly no issue of information loss like I described. I mean, if you don't have a black hole, this whole issue in question doesn't arise. Yeah.
So, question on this, maybe addressed somewhat to the fuzzball people. I think there are 2 variants of this. One is where you just stop at the horizon, and the other is where you actually do form a black hole, so this doesn't happen, and then you turn into a fuzzball later, and it depends on the timescales that you don't quite know what they are. I've heard both variants over time. I don't know whether they're still represented. Do all the fuzzball people agree to this picture now?
Well, I wasn't really intending to commit on when this took place, but my comment here that you only see the first half of the sentence on is that Bill already gave the F equals MA reasons why this is awfully hard to swallow. But if you, sort of form a black hole and, of course, before or maybe in the semi-classical picture around while you're forming a singularity, you do some tunneling, the point is that the rest of the sentence is that if you don't do it at exactly this stage, then you're talking about not only a major violation of classical general relativity in a low curvature regime, some, well, not necessarily so much quantum field theory, but you're also talking about a major violation of locality and causality in a low curvature regime, because you're tunneling if you form the black hole and then you're somehow going from here, to out here. I mean, you're really going backward in time.
Can I answer Steve's question? Essentially, there are two ways of thinking about. Some people have told me that it's the same physics. One of them is that indeed, when you go to the horizon, you have so many states and you tunnel into them. The other one is that you keep on falling, and then at some point you go to some region where you excite these fuzzball degrees of freedom, which have very low energy.
Right, but you're talking about over here, you're exciting the fuzzball stuff.
Yes, because you have very low energy. Essentially, by the Heisenberg uncertainty relation, delta A, delta T is over the h bar. And if your delta E is very, very small, your delta T is going to be very large, and you'll have fluctuations even backwards in time. It's much less plausible, but it's something which I cannot rule it out. Just because when you have low mass of freedom,
just claim unequivocally that there are no phenomena in quantum field theory that are genuinely acausal. So you're talking about a major violation of known quantum field theory. Now, those are the only assertions that I'm making. This is a radical alternative that is really talking about making major violations, major non-trivial violations to probably both classical general relativity and quantum field theory in a very low curvature regime.
Though a tiny comment, and that is, in this context, I don't think non-locality implies acausality. That's something we usually infer by, using the symmetries of, say, Minkowski space, and they're different here.
Okay, I'm not really making a distinction between causality and locality in this, but I mean, it is a major, transmogrification of known theory. Okay. Okay, so if we do form the black hole, or at least what looks like a black hole for a while, we've got modifications here and here to go, then my logically second possibility is that this picture is the original picture that I've drawn, which is mostly reproduced here. Major changes take place or the picture is wrong in this region too. And that, I think is maybe not quite so radical, but certainly a comparably radical alternative, because whatever you're doing, you're definitely ultimately talking about destruction of the entanglement between the inside and outside of the black hole here in this evaporation regime, again occurring in at least beginning and continuing in some basically arbitrarily low curvature regime, depending on how big a black hole, big a mass you started with. And that's going to, in some way or other, the details of that have been spelled out in arguments we've been discussing this whole week, but in some way or other, that's basically guaranteed to give you a singular quantum field state if you can describe the state in any kind of quantum field way on the horizon. So I would claim that just on these grounds alone, any solution that involves modifying the semi-classical picture in this region 2 is going to necessarily, give you some sort of singular state at the horizon. What I want to emphasize is that clearly seems necessary. It's not the least bit obvious to me that that's anywhere near sufficient to merely just have a singular state near the horizon. Doesn't seem to me to be anywhere near sufficient because of the situation where you've formed the black hole with matter that's highly entangled with matter outside the black hole. Destroying the short distance entanglements here is not going to help you get that out. Now, complementarity and other things, which are also, I think, major modifications of known, quantum field theory, quantum physics, etc., can certainly help with that. But I'm just saying that this firewall is, well, I'm arguing that it's necessary, but not at all sufficient. Okay, I think I can go quickly between 3 and 4 on these possibilities 3 and 4 to get them out of the way, because I haven't really heard any advocates of those possibilities at this meeting. So one possibility, the third possibility is that you've got a major modification of this picture near this final pop, a Planck time or so away from the final evaporation, and in fact the black hole doesn't evaporate, but I've continued the horizon. I should also continue the singularity up there forever. And then in some sense, at each time, I could draw a slice that goes into the black hole and gives me a pure state. I would have Hamiltonian evolution in, pure state goes to pure state if I included the part of the slice that goes into the black hole, no matter how late that was. So, that would keep evolution unitary, but I mean, it's far from clear to me what this remnant scenario, what good it would do you as far as this is concerned, because although formally you'd have on a time slice, a unitary evolution, you still have, if you're up here, you have absolutely no access to all the stuff in here that your stuff out here is entangled with. So why you would feel a lot better knowing that the remnant is still around, even though you can't access the degrees of freedom that it was entangled with, but knowing that it's still there rather than it's gone. Then there are further problems with this. Thermodynamic problems with these objects that have, formed with arbitrarily many degrees of freedom or whatever and are still around. Anyway, I don't know of any present advocates of remnants, so I'll dispose of or go on from there. And the fourth possibility, the remnant idea is certainly not at least a radical idea in that it involves a modification of this picture in a regime where you wouldn't have expected it to be valid. And finally, this burst scenario, which is the last possibility, is modifying the picture near the singularity of what you thought was the black hole, which is also certainly not a radical modification of anything. You wouldn't have expected your semi-classical picture to be valid here. And as a result, the stuff really never goes into a singularity. It's just caught in this region behind what you thought might have been a horizon for a very long time, and then it all comes out at the end. The major problem with this that was alluded to in questions in Bill's talk is now you're talking about arbitrarily large amounts of entropy, information, whatever you want to call it, coming out with an external mass of, Planck mass or so. The only classical or the only semi-classical kinds of states that have very high entropy at very low energy are incredibly long wavelength states. So the only way this could possibly work is if this burst stays totally non-classical, semi-classical, et cetera, until it's, gone out to Hubble radius or so. I'm just making that up as and then it could become classical and you could count up its entropy. Again, I don't know any present advocates of this scenario. Okay, yeah. Yeah. No, Ashtakar's picture, I'm going to talk further with him about that, but that's in, of course, a 1+1 dimensional model, which is fine. That would really correspond to this burst scenario, where the stuff, but there you don't have a kind of, in the 1+1 dimensions, a kind of size, amount of entropy, a priori restriction. Excuse me? Well, it may not look explosive to the observer here. There are a lot of significant differences in the 1+1 dimensional case and so on, so it's not quite really this space-time diagram. But in my classification, it definitely would correspond to this burst idea, but with the burst certainly having different properties in the 1+1 dimensional case than what I'm considering here. Yeah?
There and here, really, you end up with something like a long-lived remnant in any reasonable scenario. So you're going back to your previous.
Well, it's a little different because I think you've got to get something that expands out to huge radius.
Well, that one way to
in a very non-classical, semi-classical way.
No, sorry. You can have, if you have a Planck mass worth of energy and you have to send out all this information, you can do it if you do it over a very, very, very long time. That's why you have a long-lived remnant.
Okay. I mean, that's... Anyway, I haven't heard the case made for this, and I'm certainly not making the case for this, so I don't think we need to belabor. Well, yes. No, I'm serious. I mean, here is the semi-classical picture, and I don't see any way. It's not going to help to modify things here. It's not going to help to modify things only here. It's not, So these are the only places I would claim. The question is, what's wrong with this picture? And these are, I would claim, an exhaustive set of possibilities. I mean, of course, you could have things going wrong in 1 and 2, or if it goes wrong in 1, you don't have the rest. But you could have things go wrong in 2 and 4 or whatever.
Bob, remember to keep track of the clock, and don't take questions if you don't feel you have
No,
time.
that's fine. I think we're doing.
Okay. Bob, I just think one of the things you've already mentioned should be listed as a 5th possibility, namely the breakdown of quantum field theory at large distances and low energies.
Yeah, okay. So I guess maybe I'll draw 5,
So there's a 6th we were just discussing sometime back, which is that there could be very small corrections in region 2 that get all the information out. And those small corrections could get the information out. Those would be acausal, and you'd have to describe them in some way. But if they're exponentially small, that may be okay.
Yeah, okay, but I think that would correspond to some.
Didn't
That's
Samir
not
sort
a large
of prove
violation
that you
of
can't do
effective
that?
field theory.
I mean, Samir sort of proved you can't do that, right?
No, I think that's not right. I mean,
Yeah.
we can.
Okay, I think this argument I probably better cut off given Joe's comment.
But may I just clarify that, since that's something, first of all, not necessarily acausal, and second of all, with relation to what you said, I think not necessarily singular.
Okay. Anyway, I don't think there's, taking into account all the recent comments and so on, I mean, you can make little changes and improvements or modifications to what I'm saying, but I think this does pretty much, I think I've covered the bases, and I don't think there's anyone who is very happy. Well, there may be individuals who are very happy with any one particular one, but I don't think any of these would get a majority vote of they may get a majority vote of that's what happens, but that's what happens and I'm very happy with it, if that's what we're voting on. Okay, so that's all that I'm trying to say here. Okay, so I mean, that should settle the question. The only thing left, since I think, again, overwhelmingly majority is probably unhappy with each of these, even if they believe them, that leaves information loss. So why am I the second person making an argument for information loss out of however many speakers we've had so far? And I don't think there'll be any more next week. Okay, so there are basically 3 arguments. I mean, I've been, involved in these debates for, 35 plus years or whatever. I'd say there are basically 3 arguments that have been made, against the information loss picture that have driven people toward these drastic possibilities that I've been talking about. So the first one goes under the name of violation of unitarity. I don't like that terminology very much because, unitarity has sort of 2 completely different meanings. One is that you don't conserve probability, and if you had violation of unitarity in that respect, I mean, that's a total disaster. I don't know how to live with that, and we'd have to do something. But that's, of course, not at all what we're talking about here. What we're talking about here is an evolution from pure states to mixed states instead of pure states that, of course, conserves probability or things of that sort. So failure of the first kind would be a disaster, but that's not what we're talking about. I claim that failure of the second possibility is something that's really quite innocuous, and that you'd expect to occur any time that the final time that you're talking about is not a complete Cauchy surface for the space-time. So what do I mean by that? Well, let's just go to flat space-time. Let's consider a massless Klein-Gordon field, free field in ordinary Minkowski space-time. And if I were to do a time evolution, this is again a space-time diagram from some usual t equals constant time slice here to some other t equals constant time slice up here, that of course would be completely unitary evolution. Pure state here would go to a pure state on this later time slice. But let me do a slightly different problem. Let me ask an evolution problem of pure state that I give you down here to a state on this hyperbolic time slice, a perfectly complete spatial slice that goes off to infinity. But of course, this becomes asymptotically null, so it actually goes off to null infinity rather than space-like infinity. And the whole point is that this is not a Cauchy surface. There is radiation that can make it out around this hyperboloid and make it out to null infinity. And the point is that if I ask for the state on this final time as I've drawn it, well, the state here is going to be entangled with the state at null infinity that corresponds to the observables that this time slice didn't capture, and I'll have a mixed state up here. This is a prediction of quantum theory. It's certainly not a violation of quantum theory. Using ordinary quantum theory, that's what you would predict. Now, this is not, you may think this is some very far-fetched, of course it's ordinary flat space-time, but we've got, if we pulled up the shades here in this room, there will be photons that are going to go out the window and in the cloudless skies of Santa Barbara go off into outer space. And if we haven't prearranged for somebody to go catch that photon, it's going to go off arbitrarily far in the universe, past our cosmological horizon. We don't have to worry about it then if we're in an expanding de Sitter universe, as we seem to be. That photon is, of course, entangled with stuff here, and we are left here in a mixed state. So why nobody has ever seen a pure state in their lives. Nobody ever will. We're always entangled with stuff that is gone away. And to be, talking about a mixed final state up here when we're not looking at all observables, because there's other stuff that escaped out, is perfectly. I mean, in this context, it's certainly perfectly fine. I don't see why it isn't perfectly fine in any other context, like the evaporating black hole, where here this mixed state here, the analog of the hyperboloid, is entangled not with stuff that escaped off to infinity, but stuff that got lost into the black hole. But, the stuff here in this picture that escaped off to infinity is just as inaccessible for the family of observers on this hyperboloid as the stuff inside the evaporated black hole is to the late time observers. So I'm claiming that this is the kind of thing that we're talking about, and this is completely innocuous as far as quantum mechanics is concerned. Now, I find it really ironic that some of the same people, as I've said here, who are very concerned that pure going to mixed is a violation of quantum theory, then go ahead and endorse some really drastic alternatives that really are violations of quantum theory, quantum field theory, or classical general relativity in a regime where all these low curvature, nothing ultraviolet particularly happening, where these theories all a priori should be valid. So I want to state on the record that I believe very deeply and firmly in quantum theory, and I'm going to continue to vigorously defend quantum theory against those who might initially have set out to try to save quantum theory, but for some reasons that I don't understand, somehow got diverted into trying to destroy it. And I mean, I think in the same vein, I mean, if we had had this workshop 25 years ago or so, let's say, it would have been a lot smaller, and I'd asked people what they were doing, they would be saying, well, I'm trying to figure out a way to get unitarity in order to save quantum mechanics. And if I ask many of the participants of this workshop what they're doing, they're saying, they would say, I'm trying to figure out how to modify quantum theory so as to preserve unitarity. And I...
Quantum theory versus quantum field theory.
Yeah. So in most cases, almost all cases, when I say quantum theory, I did mean quantum field theory. Excuse me? Yeah. There's another kind that you could use as models, yes. Toy models.
Excuse me, Bob?
Yeah.
Just in defense of these people gone wild.
Yeah.
I mean, I think the perspective of many of us is that there's a very big difference between observers in asymptotic regions of, say, flat space and cosmological type observers, such as people who might be crossing an event horizon. So it's not entirely clear how to define unitarity, or what it would operationally mean to observers in cosmology. As you pointed out, we lose information all the time.
Yeah.
But it has been a very powerful principle in the context of an S matrix.
Right. But I mean, I'm saying that it's really a pretty innocuous thing to, without changing quantum field theory at all, change the notion of S matrix if you want to evolve to a surface like that. And of course, you can't evolve backwards, but you know, if you go from a place with sort of complete information about the state to a place with less information about the state, you can certainly evolve forward. That's not that's a quite innocuous thing.
You don't have all of Scry Plus in your.
I haven't drawn it, but this is entangled with the rest, the part of Scry Plus that's to the past of where this hyperboloid intersects it.
Right.
No, this is not. I'm not doing ADS. Yeah. Okay. All right. The second set of arguments that I think Bill addressed, but I think I'll use the time here to address some of the objections to what Bill was saying. I mean, is the argument that was laid forth particularly clearly in the Banks, Susskind, and Peskin paper, that if you had this kind of evolution from pure to mixed, that would involve violations of energy and momentum conservation. Well, I think I won't go through the fact that, this was a particular type of evolution equation they were considering, which was sort of local with no kind of memory of evaporating black holes. Certainly would have a lot of memory of at least how much energy it evaporated, if not, the details of what it evaporated. Bill already mentioned that, the issue of sort of decoherence and energy conservation. Let me not repeat that. But the bottom line is that if we just ask purely the question, does in quantum mechanics or quantum theory, any quantum theory at all, does pure goes to mixed require some violation of energy and momentum conservation? I think Bill's example convincingly answers that question as no, it is not quantum mechanics. It may be other things, but in addition to quantum mechanics or quantum field theory, but that does not imply, pure going to mixed does not imply a contradiction or a failure of exact energy and momentum conservation. Now, let me just say, I mean, Bill, faced some, fire and criticism that, his model is not a quantum field theory model. How would you generalize it to that, how would you incorporate aspects of, other aspects that one has in the black hole? I don't think that it would be easy and possibly not possible to model, all or even most of the features that are expected to occur in the black hole system with some ordinary quantum mechanical system. This is just modeling this particular aspect and no other. It's doing a terrible job in modeling other things. I think the gravitational system is genuinely different from the ordinary quantum field, in flat space-time or whatever situations, in that the black hole really does, leave outside precisely what its energy and momentum is. Possibly not anything else or not anything much else, no other hair. And that leaves open a perfectly good possibility for, as the evaporation continues, to conserve energy and momentum, because that's a property that is accessible to the radiation, the particle creation, et cetera, that's going on outside the black hole, whereas all this entanglement information and so on has presumably propagated deep inside and is not accessible. Yeah.
Bob, since both you and Bill have misstated what we actually said in the paper, let me tell you what we actually said, which was that we considered a large class of models based on quantum field theory, in which we tried to incorporate into the equation some degree of locality. And we said quite explicitly that if you give that up, there's no problem with energy or momentum conservation. That's said in our paper. And I think Bill's example is effectively included in our paper. If his example, I think, will satisfy the Lindblad equation with some non-local operator if you try to make his example into a quantum field theory.
Okay. Well, I have to admit that it has been about 20 years since I reread your paper, so and I certainly didn't recall that is in there, and I certainly stand corrected.
We were reacting to a particular thing, the particular idea of Stevens, that a particular kind of dynamics that he imagined that would infect microscopic physics by black hole pair creation and so forth, and that's all. That's what we were reacting to.
Yeah. Let me just say, though, in response to that whatever you said in the paper, this is how I've heard it, this first sentence is how it is reported in talks. I'm not saying by you or Peskin, but by talks by others on this subject.
Okay, but I think we need to take a more refined point of view. So this is not a good enough statement, but we should think about what models we can make that have the correct properties to describe a black hole, to fit in with other general things. It's approximately local. If a black hole forms and evaporates here, it doesn't change things far away, et cetera. And I don't think anyone has found any reasonable model that satisfies the basic needs, energy conservation, repeatability, so you can have repeated experiments where you form and evaporate black holes. I don't think there's one on the market. And I think
we're in agreement with what you're about. I mean, I would not be surprised if no such non-gravitational model exists.
No, well, gravity is not relevant if you're just looking at things asymptotically.
But gravity is potentially going to be very relevant for conservation of energy and momentum. I mean, conservation of energy and momentum in the gravitational system is preservable, in a kind of way like conservation of charge might be preservable, which you really can do very easily, but in a non-gravitational case, it's much harder because your entangled system is going to soak up some of the energy, at least part of the time.
Bob, we have to be out of the room in 12 minutes, and I want to be, I see a lot of hands.
Yeah.
And so the question is, how do you want to...
No, let me go. Why don't I go on and we can return to any of this. I don't have much more, but I don't want to cut off because... So I've already covered this. I mean, so now, the last and I think most major argument, against information loss is the ADS-CFT argument. So why do I have a problem with that, or what is, what is the situation, and why, unless I'm claiming ADS-CFT is completely wrong and nobody should pay any attention to it, why am I not won over that there really must be information loss? Because I think this is, at the present time, by far the most persuasive, or the argument that has persuaded most people. So what is the argument? Well, said in one sentence, right, if the gravity theory in asymptotically ADS spacetimes is dual to some ordinary conformal field theory with ordinary Hamiltonian time evolution, well, the conformal field theory certainly doesn't, or presumably I should probably say, doesn't have any kind of pure mixed evolution. It doesn't have black holes or anything like that that might give you that. Then that must not be possible in the bulk quantum gravity theory. Okay, so of course ADS-CFT is a conjecture, but my problem, or the reason I don't find this argument persuasive, is not that this conjecture hasn't been proven, so we don't have to pay any attention to it, but I don't really see this conjecture as having been formulated in the kind of way that one could use reliably in this argument that one wants to make. Now, what do I mean by that? I mean, if pure goes to pure in the CFT, doesn't pure have to go to pure in, the bulk theory, et cetera? Okay, so well, let's break this down carefully, which is why I wanted to leave 10 minutes at least for this. So what are we talking about when we talk about information loss in black hole evaporation? I guess I've kept you hanging here, right? Information loss is exactly the statement that if you look at bulk observables at late times, after the black hole is evaporated is what I mean by late times, that's not the complete set of bulk observables, right? So just so that I'm completely clear about that, right? If we look at the observables up here, that's not all of the space-time observables because there are space-time observables back here in the black hole that's evaporated. So if the observables here are entangled, if the state is such that there's entanglement between here and here, the state, as there surely would be in any quantum field theory-like situation, then this is the statement. The loss of information is exactly the statement that the bulk observables at late times is not a complete set of bulk observables. So information loss is a statement, first of all, about bulk observables. Okay? Now, ADS-CFT, which I'm most certainly not an expert on, but I think unequivocally would seem to assert, well, not necessarily unequivocally, I've heard possibilities that maybe not all of the bulk observables are in the CFT observables. Let me take the simple statement that if we look at all of the bulk observables, that's in a perfect correspondence with all of the CFT observables. So let me take that as given. The other thing that we know, or that I'm perfectly willing to take as given and granted, is that the CFT observables at late times, because this is an ordinary Hamiltonian system, allow you to construct all of the CFT observables. So if I know the CFT observables in a neighborhood of one time slice of the CFT, I know everything there is to know about the CFT observables. Okay, let me take that as given. Okay, but there's a key step that's really needed to complete this into some argument against information loss. One needs a step. I mean, you could possibly do slightly other formulations of this than what I've written, but you need something that says that the bulk, or if you had that the statement that the bulk observables at late times are in one-to-one correspondence with the CFT observables at late times, then you could complete this argument and say there's a real problem or a real conflict between ADS-CFT and information loss. Okay, but I don't know much about the gravity CFT observables correspondence, but I mean, the whole notion of bulk observables, in fact, is quite murky given gauge invariance and so on. But in any case, for sure, I do understand that the correspondence between bulk and CFT observables is certainly non-local in space-time. That is, you don't get, if I tell you what the bulk observables are near the ADS boundary on which the CFT lives, if I tell you what that is, those observables are near the boundary over a little time interval of the bulk, that doesn't tell you all of the CFT observables, right? There are CFT observables that certainly probe into the space-time. And as far as I'm aware, I mean, very little of this bulk to CFT dictionary is really explicitly known. So, I mean, as far as I know, I'm certainly be quite interested in hearing arguments to the, arguments to the contrary, that there's lots of room for nuances in the dictionary that would, in the case that physically corresponds to the case where black holes are present, that would allow this late time observable correspondence to fail, that the late time boundary CFT, that is, observables, are not in one-to-one correspondence with the late time bulk observables. Maybe a clearer way or an easier way to restate what I'm saying is what is there known or believed or strongly conjectured with evidence in the ADS-CFT correspondence that says that the CFT state at late times can't continue to encode the information that went into the black hole, even though that information is no longer accessible to the late time bulk observers. So if this were the case, without the question mark, then you could perfectly well have an exact ADS-CFT correspondence, exact Hamiltonian evolution of the CFT. The late time CFT state would be pure, but the bulk observers would have experienced information loss, as in the semi-classical picture. So I certainly have the feeling that not enough, attention has been paid to this basic issue and really the details of the correspondence, et cetera. It's certainly my hope that more attention will be paid, that these ideas will be developed further to make some solid argument against information loss, or maybe it'll end up being a solid argument for information loss. If one had such an argument, I mean, another very good reason for exploring that is then that argument would undoubtedly provide some explanation of how information is regained, not just that it must happen somehow or other, but we have no idea why. Until that's done, I'm certainly sticking with information loss. Thank you.
There are many people, I think, who want to respond to what you said, ADS-CFT, and they can start for the next 3 or 4 minutes. We have to leave this room sharply at 3, and we'll meet in the auditorium at 3:10. Ted Jacobson will talk. After Ted's talk, perhaps there'll be time for an extended discussion of these issues, because they needed an extended discussion. But I think Daniel was the first person who wanted the shot.
Yeah.
Well, yeah, I just wanted to suggest, there's been a decent amount of literature about the flat space limit of ADS-CFT and making small black holes by scattering experiments where you send in localized wave packets from the boundary, and then later you collect them again. So that's definitely a situation where the late time CFT observables correspond to late bulk observables, and it's hard to see how that couldn't be a unitary process.
Yeah, but we're talking about all of, a correspondence between all observables, not just some.
Well, no, but if we can get the scattering, the formation and evaporation of a small black hole and see that it's unitary, then aren't we happy?
It's fair to say there's not uniform agreement among people.
So let's see, these CFT observables or states that are not in correspondence to the bulk observer will have zero energy, right?
Well,
Well, we are talking about states, right? So there are states in the CFT which are not states of the bulk theory. and I think would not carry any energy, because like we can form a black hole and then extract the energy of the black hole.
So what I'm proposing is, in the bulk theory, they would be, the CFT state would correspond to could be expressed as some late time bulk state together with some state of what happened inside the evaporating black hole. There would be no energy, I think I see what you're saying, associated with what
so I think it's
had
the
gone
assumption
into
that the
black
vacuum.
hole.
Yeah, that's right. So the vacuum of normally we say the vacuum of the CFTs is unique. So it wouldn't allow to...
Yeah, but this obviously isn't the vacuum state, which wouldn't have had a black hole.
No, but in the end you would have the vacuum, because you can couple the CFT to some external system which takes out the energy by using observables and processes which we understand the dictionary for. And then we are left with nothing in the interior, right? And nothing in the CFT.
If we take out energy from the CFT, what's supposed to be happening to the bulk? I mean, even if we didn't have black holes?
Yeah, we were changing the boundary conditions in the bulk for some fields that we are coupling it to another system. And then both the energy and information are going to the second system.